clipboard on the screen. Okay, so today we're going to be talking about B trees, LLRBs, and hashing. Okay, and I have prepared slides, which is different than usual because I usually do it on my iPad. So we'll see how it goes. Okay, so this is going to be like hopefully a fluid introduction about why we're using like LLRBs to begin with. Okay, so why can't we just keep using a regular binary search tree, right? There must be some problem with the binary search tree if we're putting all this effort into like working with LLRBs. Okay, so the problem with binary search trees is if we keep inserting numbers in increasing or decreasing order, the tree becomes really spindly. Okay, and what this means is it just becomes like a linked list in terms of like additions or deletions, right? So the runtime is awful. So the problem is that the tree isn't bushy. And this is a crazy idea, but what if we don't add any new leaves, right? The problem here is we just keep adding new leaves, and that's bad. So a 2-3 tree is going to solve this problem by not adding new leaves. It seems kind of crazy. So let's see how that works. Okay. So when we're working with a B tree or a 2-3 tree, we're going to overstuff the current leaf nodes instead of creating a new leaf node. Okay. So let's say that we have the number 1 in our 2-3 tree. Okay. When we insert the number 2, what's going to happen is instead of creating a new 2 node, we're going to overstuff this 1 node. Okay. Nice. So now what happens if we insert the number 3? Okay. We insert the number 3 and we see the size of this node becomes 3. Okay. In a 2-3 tree, the maximum size of a given node is 2. So how do we solve this problem? Well, what we do is we take this middle element in this 2-3 node and we push it up. Okay. So what happens is we have this overstuffed node, right? The maximum size of a node in a 2-3 tree is 2. So what we're going to do to solve this problem is push the 2 up to the layer above it. Okay, and now we have a balanced binary search tree. Okay, so let's see what happens. If we insert 4, right, we go to where 4 should go and we overstuff the leaf node. Then we insert 5. What happens is this leaf node becomes overstuffed, so we promote 4 to the layer above. Now what we can see is we have 2 and 4 are hanging out together, and that's totally fine because the node size is 2 and it's not 3, right? Okay, so let's do a couple more. So let's say that we insert 6 and 7. What will happen here is we overstuff this leaf node again, then we push 6 to the layer above. Then we see that 2, 4, and 6 is now overstuffed, so we push 4 to the layer above, and we get this tree. Okay, so this is how a 2-3 tree works. We keep overstuffing the leaf nodes. If a leaf node or any node ever exceeds size 2, then we promote the middle element to the layer above. Okay, so I'm going to quickly talk about some invariants about B trees, and then I'll open the floor for questions. Okay, so what is an invariant? An invariant is something that always holds true. And it's really helpful when we work with these data structures to think about these invariants because it allows us to see if we're actually doing things correctly. Okay, so a node in a 2-3 tree can be of size at most 2 and have at most 3 children, right? That's like looking off the old example. And this one, the second thing is not as intuitive. When we work with a B tree, all the leaves are at the same depth. Okay, that's really, really powerful. What that's saying is our B tree will always be balanced. Okay, so take like 30 seconds and try to prove to yourself why this is true. Why are all the leaves always at the same depth? Okay, does anyone want to volunteer an answer? Okay, I'll give my answer then. That's totally fine. So, oh, okay, Anne, you got it.
Okay, so I feel like with B trees, like whenever you try to like stuff in nodes or keep inserting nodes, then each like node can hold at least like 3 elements, and then once you hit 3 elements, then it moves the middle node up, and then every time it does that, it basically ensures that the left and right sides are balanced.
Yeah.
That's how I interpreted it.
Yeah. Perfect. Just like kind of going off that, the only time we ever increase the height of a B tree is when the root node is overstuffed. Do you guys see that? That's the only time we ever increase the height of the B tree, because we create a new root, right? So if you guys look at this operation of pushing that middle element of the root up, all of the other elements, right, just increase their height by 1, right? So you guys kind of see here that 1 is like 1 away, 3 is 1 away. So now after increasing the height by 1, right, all the leaves are still at the same depth. Okay, nice. So why are these like invariants helpful? When we're working with B trees, it's a good way to check our work by making sure these two are true. Okay, nice. Okay, any questions on 2-3 trees?
I had a question about implementation, if that's okay.
Okay, I'm gonna sidetrack your question.
Okay.
Like these 2-3 trees are really, really hard to implement, right? Like it looks hard to implement if you're like looking at this. So we actually like, we're not gonna implement them in this class, but we're gonna provide a different way of like exploiting the same benefits of a 2-3 tree. That's what an LLRB is. So does that sound good? Okay. Any other questions? Nice. Okay, so with this understanding of 2-3 trees, the problem, as Kush brought up, is that these are really hard to implement in code, right? Like imagine like having some data structure, I don't know, it's like a list where you're storing a bunch of elements. It's kind of complicated. So what we're gonna do is we're gonna create this thing called a left-leaning red-black tree, okay? A left-leaning red-black tree corresponds identically to a given 2-3 tree, okay? So looking at this 2-3 tree, right, what we're gonna do is every node, right, that has 2 elements, we're gonna break it into 2 different nodes that are connected with a red link, okay? So looking at this 2-3 tree here, what we see is that this 1-3 node, we're gonna break it into 2 nodes, 1 and 3, that are connected with this red link, okay? And the same logic applies for when we look at this 8-9 node. What we're gonna do is we're gonna represent it in the left-leaning red-black tree as these 2 nodes connected with a red link, okay? So we could think about a red link as it's basically gluing together 2 nodes, right, that are actually part of the same node in the corresponding 2-3 tree, okay? So what does left-leaning mean? If we look at any red link, okay, any red link, it's always pointing to the left, okay? So what that's saying is if we ever have a 2 node, let's say 8, 9, we know how that looks in this left-leaning red-black tree is 9 is up here and 8 is to the left, okay? Maybe like the video mirrored my image, so I apologize, but it worked for me. Okay, nice. So let's look at like how we do insertions and deletions in a left-leaning red-black tree. Okay, so how inserting in a left-leaning red-black tree works is we do the same exact thing as we were inserting in a 2-3 tree, okay? And a general rule of thumb, a 2-3 tree is the same as a left-leaning red-black tree. It's the exact same, just a left-leaning red-black tree is implemented using like red links instead of like putting the 2 elements in the same node, okay? So let's say that we want to insert the number 0. What we do is we want to attach it to the same node as 1, right? If we're working with the 2-3 tree, what would happen is we would put 0 right here, right, in the same node, okay? So how we do that in the left-leaning red-black tree is we make it the left child of 1, and we give a red node, a red link, okay? Because now you can kind of visualize 0 and 1 are together. That's the same exact thing that would happen in a 2-3 tree, okay? But sometimes insertions get a bit complicated. So let's see about that case. Let's say we add the number 4. What happens here is we want 3 and 4 to be hanging out together. So what we do is we create a red link between 3 and we make 4 a child, right? The problem here is that in a left-leaning red-black tree, our life is so much easier if we make it such that all red links go to the left, okay? It just makes our life easier, and you guys will see that. So right now we see that this isn't the case, right? This should be, the red link is pointing to the right. Okay, so how can we solve that? So there's different ways that we can solve this, okay? So how we solve this is we use this thing called rotations, okay? A rotation is really cool, and what it does is it mutates the tree while preserving the property of being a binary search tree, okay? So let's say that we have A and B, okay? And B is the right child of A, okay? What's going to happen here to solve the problem that we saw before is we can rotate A to the left, okay? So now what happens is A will be the child of B, okay? And what happened here is we solved the problem of having the red link go on the right. Do you guys see that? Now, if we say A is the left child of B, we see that the red link points to the left. Okay, but we still have to deal with the children of A and B, right? So how do we deal with the children? Well, we can kind of put them in 3 buckets, okay? One bucket, we'll call it X, is the subtree that's all of the things that are less than A. We can look at the bucket Y, which is all of the elements that are between A and B, and we can look at the bucket Z, which is all the things that are bigger than B, okay? After setting A to be the left child of B, we need to reassign X, Y, and Z, right, to be the correct positioning, okay? So we know that X is less than A, so we'll set X as the left child of A, right? We know Y is in between A and B, so we'll set Y right here, and then Z is greater than B, so we'll set it here, okay? So after doing any rotation, we have to deal with the children of A and B, and that's how that works, okay? So I'm going to quickly go over rotate right, and then I'll take some questions. So rotate right is the same exact thing. What's happening here is now we're rotating B to the right. So what that means is that if A is a child of B, after doing rotate right on B, now B is a child of A, okay? And a good way I like to think about it, it's hard for me to like show you guys because of the mirror and camera, but like you take like the 2 nodes and you kind of just rotate them like that, you know? So you take the 2 nodes and you like rotate them. That's like I like look at it and it kind of makes sense. Okay, so rotate right is like symmetric is rotate left. And you guys will see more applications on how we use these to mutate the tree. It may not be like immediately apparent, that's totally fine. But I'll open the floor to some questions right now. There seem to be a lot of things in the chat, but you guys can. Oh. Okay, I can mirror my video. Okay, if you guys have questions, like feel free to like interrupt me. Sometimes I don't see the chat, as in usually I don't see the chat. Okay, questions.
Can you explain why the bucket of where Y is located, how that became from A's child to B's child?
Yeah, exactly. Okay, so when we think about rotating right on B, we see that A has 2 children here, right? And now A only has 1 child, right? Because now B is one of his children. So we need to have some place to put Y, okay? If you think about Y corresponds to all of the elements that are less than B and greater than A, okay? So this subtree rooted at Y is all of the things that are less than B and greater than A, okay? So when we want to put it in the correct spot in the new tree, all we have to say is, right, we go less than B and greater than A, which is exactly what we're doing here, right? Greater than A, less than B. Same thing. Is that gonna make sense? Okay. I'll do one more explanation and then we'll move on. So Y contains all of the elements that are less than B and greater than A, okay? So in the new tree, we have to put Y in its correct spot, okay? So if we're looking at all the things that are less than B, right, to the left of B, and greater than A, right, that's where Y goes. Okay. So hopefully that made sense. No worries if it didn't. You can maybe like watch this or like watch Hug's explanation again. Okay. Any other questions?
Is this just an example of like rotating right, or is there a reason why we're doing this? Because
Yeah.
now we have a right-leaning left, right-leaning red thing.
Okay. Yes, this is like just an example of like how a rotate right operation works. I still haven't explained like why they're actually useful. So good question. You'll see that in like a couple slides. Okay, let's keep going just for the sake of time. So the last operation, right? This is a 2-3 tree. A left-leaning red-black tree is the exact same as a 2-3 tree. It's just now we have red links and stuff, okay? So if you guys recall, in a 2-3 tree, a common thing that we do is promoting the middle element to the layer above when we need to when the node is overstuffed, okay? Do you guys remember that? Like if we have a node containing 1, 2, and 3, what we'll do is we'll promote 2 to the layer above, okay? So there must be an equivalent operation in a left-leaning red-black tree because they're basically the same thing, right? So let's say that we have a left-leaning red-black tree that has a node, right here, that's of size 3, okay? Do you guys see that? How 2, 1, and 3 are all like hanging out together. It's overstuffed. How we solve this, it's actually like quite remarkable, is we're going to invert all of the colors along this 2 node, okay? Do you guys see that? So if we look about what happens is we see these 2 nodes become black and the link above becomes red, okay? So right, these 2 links become black, this link becomes red. And what that's doing, it's pushing 2 to now hang out with 4. Do you guys see that? That's the exact same thing what would happen in the corresponding 2-3 tree, right? In the corresponding 2-3 tree, we would have 4, then 1, 2, 3, and then 6 here. And then this node would be overstuffed, so we'll push 2 to the layer above. The exact same thing is happening here. It's just done in a really slick and like surprising manner, where all we need to do is color flip all of these links. So the act of like promoting or pushing up the middle node in a node that's overstuffed is called a color flip, because we're flipping all of the links around too. Okay. So you guys will see like an example of all of these. We'll go over some problems, but there's two more things I want to go through. So the question that was brought up is, why do we care about rotations in left-leaning red-black trees? Okay. So a common example of a rotate left is that we have 3 as the right child of 2, and then we rotate left on 2, right? That's one common example over here. Another common example, surprising, is let's say that we have 3 and 2 hanging out together here, and then we insert 1, right? We see here that this node containing 1, 2, and 3 is overstuffed, okay? So what we want to do is eventually do a color flip on this 1, 2, 3 node, because that's how we resolve nodes that are overstuffed. But the problem is, if you guys remember over here, in order to do a color flip, it has to look exactly like this, right? It has to look exactly like this. And right now, if we're looking at this node, it doesn't look like that. So what we do to prepare for the color flip on 2, we will rotate 3 to the right, okay? Do you guys see that? If I rotate 3 to the right, what's happening is we're preparing for a color flip, right? Now our tree is in the exact state that we want it to perform a color flip on 2 and thereby promote 2 to the layer above, okay? So these are 2 common situations when we'll do a rotate left or rotate right. So yeah. Okay, the last thing, key takeaways. So what are the invariants with left-leaning red-black trees, okay? So if we ever see these are some problems, okay? If we ever see a right-leaning red link, that's a problem. How we deal with right-leaning red links is by doing rotations, okay? If we see a node that's overstuffed, we do a color flip, right? So when you guys are working with insertions, you guys should check these 2 things. If this is true, something's wrong, right? If the node's overstuffed, something's wrong. Then after we do any insertions, we should check our work by 2 things. It should still look like a binary search tree, right? If you look at all of these examples, these are binary search trees, right? They just have red links at some places. So checking our work is just making sure it looks like a binary search tree. Another good way of checking our work is by the same logic of a 2-3 tree, is all the leaves should be of the same height, okay? Right, that's the same logic of the 2-3 tree. Except now, to say that red links don't add to the height, because like if I have two nodes here, they're technically all on the same level, right? If they have red links between them. Okay, exciting. So that only took me a long time. Unfortunate. Okay, so this is the first question on the worksheet. We have an excellent like animation, but before we get to that, I want you guys to like spend 5 minutes and try these insertions, okay? And I can also answer some questions. So ask away.
This might be a silly question, but I just want to double check my facts. Sure. So so a left-leaning red-black tree, it's like a type of binary search tree, but a 2-3 tree, that it's not a type of binary search tree, right? It's kind of like its own thing, or I don't know.
So like you can think about a 2-3 tree. It is like a binary search tree. Now we just have the idea that like a node can have multiple elements, right? So it's not like, it's a little like untraditional in that manner, but we still follow the same properties of like, if something's less, we go to the left, right? If something's greater, we go to the right. If something's in the middle of two like nodes, then we go like to the middle child, you know? Like if we have like the node consisting of 1, 4, and we try to insert 3, what we'll do is we'll go to the in the middle child of 1 and 4, right? So it's like the same properties of binary search tree. It's just a little untraditional. Yeah.
Do we always split the middle person? Like when we that's just
intuitively should also make sense. If we split the middle, right, it maintains the property of being balanced. Because if we have like a 3 node, we split the left guy, then like our whole tree is just leading to the right. Do you see that? Like putting the middle up, it just makes life like a bit more symmetric. Yeah. Nice.
Thank you.
Yeah, you're welcome. Okay, hello. So we're going to be going over question 1. And the first thing we want to do is insert 7. As with any insertion, what we're going to do is create a red link, right, between the node we're inserting and the proper spot in the tree. Okay. And right, if we look at this tree, everything is perfect. Okay. What do I mean everything is perfect is all the red links are pointing to the left. All the leaves are the same distance from the root, right? 1 is one black link away. 9 is one black link away, right? Everything is good in our LLRB. Okay, so then we insert 6. So what happens when we insert 6 is we see here that we have this overstuffed node consisting of elements 6, 7, and 9. To address this problem, we eventually want to color flip, but we can't color flip quite yet because it's not in the correct configuration, right? So what we need to do is rotate 9 to the right, okay? Now we see this is the state of the tree, and we can color flip on 7. So we color flip on 7, and now we see that 5, right, at the top of our tree, we have one node consisting of 3, 5, and 7, right? Imagine the corresponding 2-3 tree. We have 3, 5, and 7 at the top. So what we want to do, in this case, the root node is overstuffed. So when the root node is overstuffed in a 2-3 tree, what we do is we push 5 to the layer above it and create a new node for 5, okay? The same thing happens here, and we just color flip on 5, and we just change these lines to black, okay? And if you guys like are kind of iffy, like think this is iffy, go to the 2-3 tree, you'll see that this is exactly what happens. Okay, so now we have a left-leaning red-black tree without red links, right? It may look kind of funky, but like it's still a valid left-leaning red-black tree. Okay. The next thing we want to do is insert 2. We see right here it's on the right child of 1. To address this, we just simply rotate left on 1. Okay, and now we have the properties back, and we're happy. Okay. The next thing we want to do is insert 8, which is just the left child of 9, totally chilling. And then the last one is kind of tricky, insert 8.5. So what happens here is we have this overstuffed 3 node, okay? This is a tricky problem, so try to pay attention. So we have this overstuffed 3 node consisting of 8.5, 8, and 9. We want to color flip, but we can't, okay? So what we need to do is we need to set up a setup to a color flip, okay? So what we're going to do is rotate 8 to the left. Now we're in a configuration that we know we can set up a color flip, okay? Right? We've seen this guy before. So what we'll do is rotate 9 to the right. Now we're finally able to do a color flip. So what we'll do is do a color flip on 8.5. Okay, now let's see, is everything happy in our tree? Well, it's not, because 8.5 is the right child of 7, and there's a red link. Okay, so to address this, all we need to do is rotate 7 to the left. Okay, so this is kind of tricky, because if we rotate 7 to the left, where do 6, 8, and 9 go? Okay, so you'll see here that we rotate 7 to the left, and now 8, right? 8 used to be the left child of 8.5. Now it's the right child of 7. Okay, and a good way to like prove this, like where do I put these numbers after rotation, is it should still be a binary search tree, right? So a good way to check is like just see, is 8 in the right spot in the binary search tree? Well, it is, right? It's less than 8.5 and greater than 7. Is 6 in the right spot? It is. Is 9 in the right spot? It is. So a good way of like, sometimes it gets confusing on like when I do a rotation, how do I deal with the children? Just make sure it's a regular binary search tree and everything's good. Okay, so that is all for question 1. Does anyone have any questions?
Could you go over the color flip 5? Like, I was confused because I saw like multiple red links to the root node, or so I was just confused what to do there.
Yeah, right here, right? So
Yeah.
here what we want to do is do a color flip on 5, okay? The reason is if we look at the corresponding 2-3 tree, how that's going to look is we have 3, 5, and 7, right? And then we have like 1, 4, 6, and 8, and 9, right? So in the corresponding 2-3 tree, what we do is we would push 5, right, above. Do you guys see that? That's what would happen in the corresponding 2-3 tree. So to make this work in this left-leaning red-black tree, we can just do the same thing, right? All we need to do is push 5 to be by himself at the top. In order to make 5 by himself at the top, all we need to do is change these links to black, right? You see how like this is the same thing? Both processes are the same? Nice. Okay, exciting. Anyone have any other questions?
One of the first slides you said like you have to check that the result is still a BST and that all the leaves are on the same level. Is that the second criteria? I didn't pay attention.
Yes, yes. So when we work with like a left-leaning red-black tree or a 2-3 tree, a good way to check your work is to make sure that all the leaves are the same depth from the root, right? Or the same height. Okay, so what does that mean? Well, let's look at like the end result here. This is our end result, okay? So we can see that this is a valid left-leaning red-black tree is because 6 is 2 black links away from 5, right? Everything, like all of these leaves, right, are all 2 black links away, okay? And if we recall in a 2-3 tree, we have this invariant that all leaves are the same depth, all leaves are the same height, okay? We can see here that a 2-3 tree and a left-leaning red-black tree are in essence the same, so we should have the same invariant hold, and we do. We just ignore red links in the height calculation. Yeah. So just like a way to check your work and something that's pretty cool. Okay, so any other
Can you
questions?
look at the last 2 slides really quick
Yeah.
from this slide?
Yeah. Okay, I'll just like walk through the whole thing quickly. Would that be good? Okay, we'll go from here.
Yeah.
Okay, these slides will also be like publicly available for all of you. I'll send the link in the chat. It's tinyurl.com/LLRB-slides. Perfect. Okay, so you guys can like look at them after this discussion. Okay, so I'm gonna share my iPad and we're gonna move into hashing for the last 15 minutes. Okay, perfect. So yeah, we're not going to get time to do question 2, but I encourage you guys to like stay back after this discussion and I'll go over it. Whoever wants to do question 2, I think it's pretty cool. So I'll stay for like an extra 15 minutes. But for the sake of like getting everything done in an hour, we're going to grind through hashing. Okay, so who has seen hashing before? Can we do a quick poll in the chat? In participants, I mean. Okay, so put a green check if you've seen hashing before, put a red X if not. Nice, okay, it's a pretty half and half. Okay, nice. So I will give you guys a quick explanation on hashing is in the span of 2 minutes. We got this. Okay, so hashing is actually, I think, a really elegant data structure. So the problem we're trying to solve is we want to store objects in some set, okay? To do this, we're going to create an array, okay? And each array is going to have a linked list coming at that spot, okay? So what we're going to do is, let's say we want to insert the number 8 into our hash map or our hash set, okay? There's certain steps that we follow, okay? The first thing that we're going to do is compute the hash code of the given object, okay? So the idea here is we want to take an object and make it into a number, take that number, go to the correct spot in the array, and then our object should be there, right? I'll say that again because that's basically what hashing is. We want to store objects in some array. And a beautiful property of arrays is that it's constant time accessing a specific index, okay? So what we want to do is take an object, make it into a number, take that number, go to the corresponding index in the array, and then put our object at that spot, okay? The problem, like 2 small problems that you guys may immediately see, is that our array is a fixed length, right? So let's say we have an array of length 4, and we want to insert, I don't know, some object whose hash code, the hash code corresponds to like the number value of the object, and we want to insert some object that has a hash code of 10, right? Let's say we want to insert, I don't know, some object that has a hash code of 10. What we'll do is we'll take 10 and we'll make it modulo the length of our array, and then we'll go to that index, okay? To solve the problem of having like a number that exceeds the length of the array, we'll just take, this is what we want to insert, and then we'll modulo it by the length of the array, okay? So in this case, the length is 4. So what we'll do is we'll get out the number 2, okay? So now, if we're trying to insert 10 in our like hash data structure, we'll go to index 2, okay? And then we'll put the value 10 there, okay? So another problem that you guys may see is, let's say we want to store the numbers 6 and 10 in our hash map, okay, in our hash set. The problem here is that both 10 and 6 both live at index 2, right? So if multiple things live at index 2, in a regular array, you can only store one thing at index 2. To solve this problem, we're going to create a linked list at each of these indices, okay? So now if we want to insert 6, what we'd do is we'd say that 6, like its hash code is just 6 because it's a number. So we'll go to index 2, then we'll insert 6 here by appending it at the end of this linked list, okay? So that's basically like how hash maps work. So this idea called a hash set, I'll quickly talk about this, versus a hash map, okay? A hash map contains key value pairs. If you guys remember the previous lab, we worked with this BST map. A hash map is the same, okay? It just contains key value pairs. A hash set just contains like keys. You can think about it, okay? But they have the same fundamental logic, okay? So let's walk through one quick insertion, okay? Let's walk through one quick insertion and then we'll take up the next question. Okay, so let's say that we want to insert the value, I don't know, let's say we want to insert the letter B into our hash map, okay? So what we'll do is we want to make this object B into a number, right? To make B into a number, I think it's intuitive to just say that B corresponds to 1 because it's at index 1 in the alphabet, right? So we'll say that B's hash code or its number is 1. Then what we'll do is we'll take 1 modulo 4, which gives us 1 back, right? We have to make sure that 1 is in the bounds of our array. Okay, the next thing that we'll do is we'll go to spot 1, okay? And then we're going to check if B already exists here. Okay, this is very important. When we work with a hash set or a hash map, we don't have duplicates, okay? So what that means is, let's say that B already existed in our hash set, okay? We're not going to deal with values. Let's just call it a hash set for now. So if B already existed here, we don't want two Bs, right? A set has a cool property where everything is unique that's there. So what we're going to do to solve this problem is we're going to iterate through this linked list that lives at index 1. And we're going to compare B to every element in this linked list, okay? So how do we compare B to each element? We use the equals method, okay? That's very important. So the steps here, let's just kind of like walk through them together. Oh no, my iPad's buffering. Okay, my iPad's kind of lagging right now. That's totally fine. So the steps that we're going to do is we're going to first compute the hash code of the object we want to insert, okay? That gives us a number. The next thing that we want to do is go to the correct bucket. I call bucket like the correct index, okay? And the example of B, we go to index 1. The next thing we want to do is we want to see if B already exists there. So what we'll do is iterate through the linked list at index 1, and we can compare B to each like item in that linked list. If B is equal, keywords using the equals method, to any of those items, we don't want to insert B, right? B already exists, so we're chilling, okay? The subtle catch is if we're using a hash map has a key to a value, right? So if, let's say B is some key, and we want to give it, I don't know, some value, maybe like 1,000,000, what we do is if B already exists in our hash map, we're going to override its old value with the new value that's given, right? Let's say that B already existed in our hash map with value 100. Now, if we want to insert B with value 1,000, what we'll do is we'll iterate through this linked list. We'll say, hey, B is there. Let's override its value with the new one that's given. Okay, so, okay. If this like all went over your head, that's totally fine. This stuff is like a bit tricky, and if you guys haven't seen lecture, like no worries. But let's take a stab at doing question 3 on exam prep worksheet. Okay, and so try doing question 3, and then I'll take questions right now too. Okay, so any questions?
Is it possible to hash like an array list? Can you, like when Python takes it, is it going to hash the address to immutable objects?
Yeah, okay. So can somebody quickly send the exam prep worksheet in the chat? And then in response to the question of array lists, so how array lists are hashed is that they take all of the values in the array list and they extract the hash code of those objects. Okay, this is like kind of beyond like the scope of this class, but if we don't have like a hash code built in, we'll go to like the memory address. Okay, but if we do have a hash code and the array list does have like a hash code method, array list hash code kind of takes like the hash code of all of the things in the array and it combines it together. Okay.
So if you mutate anything inside the list, it's going to actually change the hash code?
Yes, it'll change the hash code, which is a problem, right? You guys see why that's a
Yeah.
problem? Yeah. So a good rule of thumb is if you insert objects into any hashing data structure, don't change its hash code, because if we want to see if that object exists and the hash code changes, we won't find it, right? Okay. So
We just what we just did with the B comma 1000. This is a hash map versus hash set.
yeah. So
Okay.
yeah.
And if B is already taken up, then we would replace that with 1000 for its value.
Exactly.
Okay.
Yeah. Ooh, okay. So a good question is, can we use arrays for better runtime? Okay. And the beauty about using a linked list here instead of using an array is that an array is a fixed length. Okay. So we're going to have to resize this array if we have an array in here. And the only thing that we really care about this linked list is that we want to be able to iterate through it, right? iterating through an array and iterating through a linked list take the same amount of time, right? And insertion in a linked list is constant time, whereas insertion in an array could potentially take a ton of time if we have to resize. That's why linked lists are better here. But a good question I like to spring on you guys is why wouldn't we be insanely efficient and use like a tree, right? Like if I have like an LLRB right here, like that would be like ultra efficient, right? So we actually could use an LLRB here and life would be like pretty good. The idea is that if we have a really, really good hash code, the objects shouldn't all go to the same bin, okay? And one more thing that I haven't told you guys is if we keep adding objects to our array, it seems kind of dumb that like we wouldn't create a bigger array. So we will, okay? If we have a set amount of objects and we exceed a certain threshold, like let's say, I don't know, we exceed 40 objects, what we'll do is we'll double the size of our array and we'll resize, right? We all love resizing here. Okay, so hash maps do resize. And because of this, we're going to assume that these linked lists are pretty small. So it doesn't really matter asymptotically if we have a tree here or a linked list, because we're assuming that the linked list is small, because otherwise we would have resized. Okay, sorry, that was like a lot to throw at you guys. Okay, another question. Okay, I'll handle like all of the BSD questions at the end. Okay, we're definitely going 10 minutes over. I apologize. Okay, so for the sake of time, I know that people have things at like 5:10. So let's walk through question 3. Okay. And okay, so this question is fairly difficult. Okay. It explores a lot of nuances of hashing, and it also explores really bad practices and the results of that. Okay. So when you guys look at this hashing example, the first thing I want to preface is this is a really bad hash code and it's a bad equals method. Okay. And because of that, we're going to see unintended consequences in our hashing data structure. Okay, so let's get started. So what we're doing here is we're creating some hash map, right? Recall a hash map takes in keys and it maps it to values. Okay, so our hash map is of size 4. So let's quickly make an array of size 4. Okay, 0, 1, 2, 3. Okay, so the first thing that we do is we create a Sohum instance, right? So let's create some TA. This is kind of 61 AE, and then we'll say the name is Sohum, and the charisma is 10. Okay, and then we can create another TA object. Okay, and then this one is called Vivant, and his name is, or his charisma is 20. Okay. Okay. So the next thing that we're doing is we're going to put the Sohum instance in our hash map with the value 1. Okay. So let's walk through the steps for how we insert Sohum in our hash map. Okay. The first thing that we're going to do is calculate the hash code of Sohum. So the hash code of Sohum is basically returning the charisma. Okay. Pretty simple. So we get, right, the first thing is we see the hash code. Okay, and then we see that's equal to 10. Okay, the next thing we want to do is go to the correct bucket in our hash map. So if the hash code is 10, 10 mod 4 is 2, so we go to the second bucket. Okay, so the next thing we do is we go to bucket 2. Okay, so now what we're going to do is we're going to iterate through the linked list at element 2, and we're going to see if Sohum already exists, right? But there's nothing in our hash map, so there's nothing to iterate through. So all we do is we insert, okay? So let's insert, we'll insert Sohum with value 1, okay? Nice. So we'll say that this is the key and this is the value. Nice, okay. So we can perform the same logic and we'll insert Vivant at the top, right? 20 mod 4 is 0, and then we put Vivant here. Okay, perfect. And then we'll say that the value is 2. Okay, so now things are going to get a bit weird. Okay, so the next thing we do is we increase his charisma by 2. Okay, this is problematic because the charisma is the hash code. So if we change the hash code, we're going to change where we look if we want to do anything with Vivant in the future. Okay, so now Vivant's charisma is 22. Okay, so now what we're going to do is we're going to reinsert Vivant in our hash map. Okay, so how we do this is we say, Vivant, what's your hash code? His hash code is 22. What bucket does that correspond to? It corresponds to the bucket 2. Okay, so what we're going to do is we're going to iterate through this bucket. We're going to say, is this object that's already here equal to Vivant? It's not, because Sohum and Vivant aren't equal because they share different first letters, right? This is a bad equals function, but we still see that they aren't equal. So what we're going to do is we're going to append Vivant at the end of our linked list. Okay, so what we'll do is at the end, we'll create, okay, I'm going to move it. We'll make it down here. We'll create a new entry, okay, with value 3. Actually, let's just make it all the same in red. Value 3 that points to Vivant, okay? Nice. So the next thing that we want to do is we want to change Sohum's name to Vohum, and then we want to put Vivant in again. Okay, so now Sohum's name is Vohum. So we're going to put Vivant and the value 4, but the value doesn't really matter, as you guys probably figured out. Okay, so Vivant, his hash code is 22, corresponds to bucket 2. So we go to bucket 2, and we see here that we have a Vohum. That's the first link in our linked list. And now Vohum is equal to Vivant, right? Because they share the same first letter. So we have found an equal object. If we find an object that is equal to that we're inserting, we change the value of that object, right? So what we do here is we change the value to 4, right? Because we see like Vohum is now equal to Vivant, so we change the value of the key value pair. Okay, nice. So now what we're going to do is we're going to increase Vohum's charisma to by 2. Okay, he's done a bit better in life. Good job. Okay, the next thing that we want to do is put Sohum or Vohum back in the hash map. Okay, so what we'll do is we'll see that his hash code is 12, corresponds to going to bucket 0. We go to bucket 0, then we ask ourselves, is Vohum equal to Vivant, right? Because Vivant lives right here. And we see that Vohum and Vivant are equal. So what we'll do is we'll change the value here to 5, right? Nice. Because we're overriding the previous value in the key value pair. Okay, we're almost there. Now Vohum realized that Sohum's a slightly better name, so we go back to Sohum. Nice. Okay. So we're back to Sohum. Okay, life is pretty good. And now we insert a new TA, Shubha. So what we do is we calculate her hash code, which is 24. We go to bucket 0 because 24 mod 4 is 0. And then we ask ourselves, is Shubha equal to Vivant? Because Vivant lives there, right? We see that Shubha is not equal to Vivant because Shubha's hash code is, or Shubha's first letter is S and Vivant's first letter is V. Okay, so what we do is we append Shubha at the end of our linked list at index 0. Okay, sorry about that. So I'm too lazy to create a new TA instance. Let's just say that Shubha goes here with value 6. Okay, so this is our final hash map. We see here that we have 4 values. We have a Vivant instance, a Shubha instance, then a Sohum, and then another Vivant, right? Okay. So that's basically all for this discussion. You guys can feel free to head out. I will take questions on this hashing question, and I'll also go back